Section 3.2, Characteristics of Polynomial Functions. The learning goals for today are to define and explain basic terminology relating to polynomial functions, relate the degree of a polynomial function to the shape, turning points, end behavior, and number of zeros, use the leading coefficient to further explain the behavior of a polynomial function, relate turning points to absolute maximum/minimum or local maximum/minimum. So the bulk of this lesson is ultimately going over basic terminology and concepts that apply to polynomial functions. And so we'll start by looking at degree. Degree is with respect to a single variable polynomial function, so that means only with respect to one variable like x. It is the highest exponent on a variable within that expression. So, for example, if we took a look at this function right here, f at x is equal to -2 times x to the power 4 plus x to the power 3 plus 2, we would consider that one to be a quartic, right? Because it has degree 4, right? The highest exponent there is 4, so that's a quartic. The end behavior of a function describes what happens to the values of the function as x gets exceedingly very large or very small. So we often write end behavior as follows: as x approaches infinity, f of x approaches positive infinity, or for example, you could also say if x approaches negative infinity, f at x approaches positive infinity. Okay, so if we just took a look at this graph right here though, what would we say its end behavior is as x approaches positive infinity? Well, if we take a look, as x approaches positive infinity, the function gets more and more negative. So we would say as x approaches positive infinity, f at x approaches negative infinity. Now, as x approaches negative infinity, f at x approaches, and so if we go backwards, right, we can see that the function gets more and more positive, so therefore approaches positive infinity. So that's the end behavior of the graph that we see right here. Let's look at leading coefficients because they're exceedingly important in looking at polynomial functions. The leading coefficient is the coefficient in front of the term with the highest degree. So it's usually the first term in a polynomial function. We usually put the degree, or rather the term with the highest degree first. Basically, the leading coefficient is very important because it determines if an even degree polynomial function will open up or down, and it also determines end behavior. So, for example, the leading coefficient in this polynomial function is -2 because it is the coefficient in front of the variable with the highest exponent, right? So that's quite important. Given that this right here has a leading coefficient of -2, this tells me that my function is going to open down. Okay, so that my quartic function is going to open down because of the -2. We'll get into that a little bit more later. Take a look at turning points. Turning points is the point in a function where the slope changes from positive to negative or vice versa. So a polynomial function can have n-1 turning points maximum, right? Where n is the degree of the polynomial. So n is your degree of the polynomial. So for example, if you have degree 2, which is to say a quadratic, the maximum number of turning points you can have there is 1. If we were to take a look at this, we can see how many turning points there are here. We see that as we go from negative to positive right here, so as we go from left to right, the graph goes up to a turning point located right there. And I'm just going to circle it right here. We've got a turning point here, a turning point here, a turning point there, and a turning point there, right? At the first turning point, our graph goes from a positive slope to a negative slope. then our next turning point, our graph will have a negative slope to a positive slope, so on and so forth. So in this case, we have the function has how many turning points? Well, we've got 4 turning points, right? And if we were to see, take a look at the degree here. Well, we see that the degree is 5, right? So the degree is 5, and so therefore, yeah, it had a maximum of 4 turning points. All right. Okay. Local maximum and minimum. A local maximum and minimum is a point that has the greatest or least value of the points in its surrounding neighborhood. On a graph, a local maximum will look like the top of a hill, while a local minimum will look like the bottom of a valley. An absolute maximum or minimum is the greatest / least value reached by a function throughout its entire domain. Indicate the local and absolute maximum minimums on the graph below. So if we were to take a look at this one, this is an odd degree polynomial. So I'm just going to write that below here. This is an odd degree polynomial. And if we look at the fact that it's an odd degree polynomial, we will see that it will have no absolute maximums or minimum. So what I'm going to do is I'm just going to zoom in on this graph. So if we look at this graph here, the reason why it has no absolute maximum or minimum, and let's write that in, so it has no absolute max or min, because the y values will span all real values, right? So y will actually go to positive infinity and y will go to negative infinity. So there's no absolute maximum or minimum on this graph. There are, however, local maxima and local minima. And so what I'll do is I'll put red here for the local maxima. Okay, that's a local maxima. Okay, and that's a local maximum. And these in green are your local minimum right there, right? Because they're the lowest points in the surrounding neighborhood, right? If we were to take a look at the graph right beside this, this is a quartic. Now, quartics will have, they'll generally have an absolute minimum or an absolute maximum. And so because this is an even degree polynomial, there will be an absolute maximum or absolute minimum, depending on how it's opening. So in this case right here, the absolute minimum, and I know it's an absolute minimum because it is opening up, that's located right here. That's your absolute minimum. Then this right here becomes a local maximum, and this trough over here, okay, that becomes a local minimum right there. Now looking at zeros. Zeros are basically x-intercepts, and they are when the value of the function equals to 0, right? So when f at x is equal to 0 is your x-intercept, or your 0. And a polynomial function can have n distinct zeros, again, where n is your degree of your polynomial. Right, so that's your degree of the polynomial. If you have an odd degree function, you must have at least one zero. That's because all odd degree functions will pass through the x-axis at least once. Even degree functions, they can have at least one, but they also have the possibility of not having any, right? So if we take a look at the first graph given here, this is an odd degree polynomial, and we can see that it has, it's a quintic, which is to say that the degree of this polynomial is 5. and it passes through the x-axis 3 times. Okay, so it has 3 zeros. Now it can have up to 5 distinct zeros, but in this case it has 3. If you take a look at the bottom one, however, the bottom one is an even degree polynomial. It's a quartic. It has no zeros, and that's because it opens up above the x-axis. So it won't cross the x-axis and therefore has no real zeros. In general, polynomial functions are continuous, smooth curves with no cusps, asymptotes, or breaks. Okay, let's take a look at odd degree and even degree n behaviors. So, an odd degree function, so basically a polynomial function with degree 1, 3, 5, 7, etc. It has opposite n behaviors, and what we mean by that is that if the leading coefficient is negative, right, the function extends from quadrant 2 to quadrant 4, right? So for odd degree functions, if it has a negative leading coefficient, so let's write that in, if it has a negative leading coefficient, it's going to go from quadrant 2 to quadrant 4, right? It's going to span all the y values, but as x goes to negative infinity, it's going to be increasingly positive. As x goes to positive infinity, it's going to become increasingly negative. Now, same thing for an odd degree function. If the leading coefficient is positive, however, right, so if we have a positive leading coefficient, it extends from quadrant 3 to quadrant 1. So as x gets increasingly negative, the function gets increasingly negative, as we see right here. As x gets increasingly positive, right, towards positive infinity, f at x goes towards infinity. Now, an even degree function has same end behaviors, all right, and that means that if the leading coefficient is negative, the function will extend from quadrant 3 to quadrant 4, right? What I like to say this is, how I like to rephrase this is that if the leading coefficient is negative, it's going to open down. That might be an easier way of saying it. So open down is with a negative leading coefficient. Now, if the leading coefficient is positive, the function extends from quadrant 2 to quadrant 1, so it's going to open up. And that's if it has a positive leading coefficient. Now, with respect to symmetry, most polynomial functions have no symmetrical properties. They are not symmetrical on the y-axis, nor do they have rotational symmetry. Only functions, however, with even degrees may be symmetrical in the y-axis, so even functions. Not all functions with an even degree are even functions, and recall that even functions have this characteristics. F at negative x is just equal to f at x, right? So only even degree functions may be even functions. But that being said, not all of them are. Next, only functions with an odd degree may have that rotational symmetry about the origin, which means that they can rotate 180 degrees around the origin and map onto themselves. Not all functions with odd degrees, however, are, and recall this is the characteristic, right? So odd degree functions, negative f at negative x is equal to f at x, or another way of saying that is f at negative x is equal to negative f at x. So either way is fine. For the following graph, determine whether the function is of even or odd degree, whether the leading coefficient is positive or negative, and the lowest possible degree of the function. So the first thing I do when I take a look at this function is I'm going to look at the range, and I see that the range spans all real numbers. So the y values can be all real numbers. There's no absolute maximum and no absolute minimum. So let's write that in. So range is y element of all real numbers. And what that tells me, there's no absolute maximum or minimum. Well, that tells me that it's going to be an odd degree polynomial. The other thing that I see here that confirms that this is odd degree is that the function doesn't appear to open up or to open down. So it can't be an even degree polynomial. Now, I also see that it spans from the second quadrant to the fourth quadrant. So that tells me something about its leading coefficient. So if we look up here, let's go back to our notes. If it goes from second quadrant to fourth, it should have a negative leading coefficient. So therefore, it should have a negative leading coefficient. And then it says the lowest possible degree of the function. Well, I'm going to use turning points for that, right? So that means that, let's see, I have how many turning points here? Well, I've got 1, 2, 3, 4 turning points. So I have 4 turning points. And recall the equation for turning points is as follows. Turning points is equal to the degree minus 1. So if I have 4 turning points, n minus 1, then the degree there is possibly 5. Now, that's the lowest possible degree, right? Because this right here, the equation for turning points is the maximum number of turning points, right? So say, for example, I had a polynomial of degree 7. Well, that means I could have a maximum of 6 turning points. But having a maximum of 6 turning points means I could also have 5 turning points, or 4 turning points, or 3 turning points. So the question asked for the lowest possible degree. And so the lowest possible degree would have to be 5, right? Because if we went lower, say for example, to degree 3, and remember it has to be an odd number, we've established that already. Well, 3 minus 1 means 2 maximum turning points, and that defies what we see in the graph. So the lowest possible degree here is 5. So therefore, the lowest possible degree is 5. Right? 3 doesn't work. There's too many turning points for it to be degree 3. And 7, that works, but that's not the lowest possible. 5 is your lowest possible degree. Example 2. Give an example of a polynomial function with the following n behaviors. So as x goes to negative infinity, f at x goes towards positive infinity, and as x goes to positive infinity, f at x goes to negative infinity. Well, if you look at those n behaviors, that's what we would call opposite n behaviors, right? Because if we were to, quickly look at this, right, that means that let me just actually write f at x there instead of y, since we're using f at x notation. As x goes to negative infinity, the function goes to positive infinity. So basically I'm going up this way. And then as x goes to positive infinity, f of x goes to negative infinity. Well, this means that it's got to be something like this. It's got to be an odd degree polynomial. And so there's many possible answers for here. But because it is going from the second quad to fourth quad, that tells me that I have to have a negative leading coefficient. So basically what I need right now is I need an odd degree polynomial with a negative leading coefficient. So the following could work. F at x is equal to negative x cubed, which kind of matches the graph that I gave there. Another example actually could be a linear function with a negative slope. And that works as well because the degree there is 1. So there's infinite possibilities here because it has to be odd degree and it has to have a negative leading coefficient. So you can come up with a bunch of them. Example 3. Sketch graph of a polynomial function of degree 4 with a negative leading coefficient, 1, 0, and 3 turning points. All right, so this has to be an even degree, which means that it's got to open up or down. But as we can see here, it's got a negative leading coefficient, so that means it's going to open down. If it has 1, 0, right? Well, 1, 0 means that it only crosses it only touches the x-axis once. So touches x-axis once. And 3 turning points. Okay, so again, there's many options that you can do here. But what I'll do is I'll show you one example of this. So you could have it's opening down, right? So it's going to go up to the x-axis, touch it, come back down, then go back up, not going to reach the x-axis, and then come back down. Okay. And this seems to match the description because we have, here is our 0, that's our 1, 0, right? It just touches the x-axis and then turns around. And here are our 3 turning points. We've got a turning point here, turning point here, turning point there. It's even degree, negative leading coefficient, opening down. So this matches all the characteristics. So just reviewing what we did today is we took a look at the terminology of degree, end behavior, leading coefficient, turning points, zeros, absolute maximums and minimums. Absolute maximums and minimums. And then we looked at the behavior with respect to leading coefficients. Okay, and the behavior of leading coefficients with respect to odd functions and even degree functions. Odd degree functions and even degree functions. We talked a little bit about symmetry. And then we looked at graphs and were able to deduce what type of polynomial functions these are going to be based on the characteristics of the graph, or opposite, given characteristics of the graph, sketch a possible graph. Okay, homework is listed there. Thanks for watching.